All right, welcome to my video. I guess this is my maiden voyage to the YouTube world. I guess just to get started really quick, my name's Jeffrey. I am a math enthusiast. I really enjoy everything mathematics. So that's kind of the basis behind why I thought about making this video, is because I want to share my love and knowledge of math with other people. So I figured this would probably be the easiest and best way for me. So I guess just along the lines of getting started, this video is more of just an informational type video. Doesn't have a lot of computations or anything of that sort. It's more of just information and basic history. So what I have in mind here with this video is providing an opportunity for people to learn about geometry and just kind of the more basic things that go along with geometry's history. And while this is a video, it could be very easily just a podcast. I do have some slides I'm going to show, but fundamentally everything just comes from what I'm going to say and what I have to say. So the reason why I did this is because I'm always looking for a video or a podcast about math, but typically I only have time to listen to things, not just sit and watch. So this can be either or, try to reach more people either way. So that's kind of the idea behind this. And just want to throw it out there early that while I'm trying to reach all audiences with this, I do have a limited amount of knowledge. I'm still just an undergrad student for right now, so I don't have a ton of knowledge, but I do have quite a bit. So I want to share that with other people, and maybe I can make a second addition to this video that will go a little bit more in depth as I start to learn more and understand more of myself. But I do have a pretty good understanding of what I want to share today, so we'll just go along with that. So yeah, I guess if you're watching this video, you're probably just like, okay, get on with the video, and so that's what we're gonna do. Let's dive into the geometry here. So I guess first we want to talk about what is geometry. There really is no point about talking about something if we don't have a basic understanding of what it is. So very basic definition. The word geometry comes from the Greek word geo, which means earth, and metria, which means measure. So earth measure is the basic idea of what geometry is. And originally, geometry was more of a practical thing to be able to measure things that were a part of everyday life. And I guess if we're going to go a little bit more in depth into a definition, just beyond this idea of earth measure, we can say that geometry is a measurement, property, and relationship of points, lines, angles, surfaces, and solids. So this basic amount or type of measure that we can do here, and how these different measures relate to us and each other. So, and I guess if we really want to see what geometry is, I feel like the best way to understand that is through knowing how geometry started and how it's developed throughout the years. So I kind of broke this down into different phases or eras of this geometric progression, I guess we could say. So I guess before we get too deep into this progression of geometry, we really can't go very far about talking about the history of geometry without bringing up the name Pythagoras. I mean, more than likely everybody's heard of Pythagoras, or at least some of his followers, the Pythagoreans. It is where the name Pythagorean theorem came from, and basically everybody's heard of that. It's something that's covered in in high school geometry. So if you put that name in front of somebody, they're going to be able to tell you whether or not they've heard about it or not, and more than likely they'll be able to tell you that they've heard of it in some way or another. So I guess just thinking about this idea of the Pythagoreans and the work they did in geometry, this is really where we begin to see geometry change from something that's more of a practical thing as far as just living day-to-day life, and that transition to more of a logical thing. So here, this first progression of geometry, we see that it's based around logical systems. So these logical systems, um, we can refer to them as axioms a lot, or axiomatic systems. This really is a big piece of geometry. And I guess before I dive too far into that, we can talk about where these axioms or this logical system idea really comes from, and that comes from somebody else that you can't go very far talking about the history of geometry without mentioning him, and that is Euclid. I mean, everything in high school geometry is based around a geometry called Euclidean geometry. So obviously, he had one or two things to contribute to the world of geometry himself. He had a massive book that was full of different geometric propositions. It had over 450 of them, and this was called the Elements, Euclid's Elements. So in this book, Euclid really takes an axiomatic look, so to speak, at geometry and a systematic look at geometry. And we could spend a whole video just talking about the work that Euclid did, and that's not really the point of this video, but I would highly suggest that you maybe pause the video or take a quick note and look up something about Euclid and the work that he put into geometry, because he really did create a great base of foundation for geometry. So before I move on, I just want to mention that throughout the course of this video, I do have a lot of things that I'll touch on briefly, but we could spend whole videos talking just about those things. So you might want to have a notebook handy so that you can write those things down and go back and look them up, because there are some really interesting things about geometry. So one more of those types of ideas really quick. You want to make sure you look up the geometry that Egyptians did, or just the math that Egyptians did in general. Those guys were the original math geniuses in my mind. They had a lot of really interesting perspectives on mathematical topics, especially geometric topics. So you want to look those guys up. But going back to just how the history of geometry has progressed throughout the years, this idea of systems is something that is very important when it comes to geometry. A system can be seen a few different ways. So just over the last few months, my focus on geometry has been largely on axiomatic systems. The basis of that is just having some undefined terms and some definitions and some axioms, and based on those things, we can develop different theorems and different ideas of how geometries will behave and how shapes and geometries behave. And that really is where geometry really begins, is through those systems. Now, while this axiomatic system has played a big part in the development of geometry itself, it probably looked a little bit different than how we view it now, but the idea is largely the same. The idea of of geometry wasn't being looked at as something that was really how to decide how big something it was. Rather, it was more logical, more based on, okay, we know a little bit about a square, so what else can we tell about a square in general going forward? Like, what different properties does it have? And just identifying the different things that we can guess and see about squares moving forward. So I guess this will lead us to our next part of the evolution of geometry is the coordination of geometry. Um, Not quite sure that's really a word, coordination, but sounds kind of fun. So yeah, we'll go with it. And you probably get what I mean. Just this idea of having coordinates in a coordinate system. So to keep going with this idea of a square, we want, besides just wanting to understand things about squares in general, we want to be able to know a little bit more beyond that. So just for example, the square, say we set it down onto what we call a plane, and we have just some generalized basic unit that's not in feet or meters or whatever. It's just sitting on a coordinate plane, and say this square that you hypothetically set down on this plane is 4 feet by 4 feet. Well, now it becomes 4 units by 4 units, and then we can generalize it even more that way. But this coordinate plane goes far beyond just setting a square down onto these coordinates and saying, "Wow, that's a great idea. This works great. We love this." Um, it allows us to be more general with any shape or any line. That helps us to decide what we can do with these different shapes and lines that may be a little bit more abstract or different than what we typically see. So this development of coordinates and a coordinate system really opens up the world of geometry in a hurry. Now, we don't only care about measure and what that is, but we also care about what geometry means for math altogether. This is really where we start to see the intersectionality of other math fields and geometry. For example, the idea of coordinates becomes crucial in the study of a new idea, which is the big one, calculus, everyone's favorite word and subject. Coordinates were so important for a guy named Fermat and his study of calculus. So I'm not going to dive too far into that, but you'll want to write that down, want to go look that up yourself. So, like I said, this is really when things start to take off. We have this idea of what you might call a normal geometry that begins to turn a little bit. And this next phase turns into a space-based idea. So this idea of space-based is really one of the more important things that arises after the coordinates are developed. So essentially what this does is this new geometry, so to speak, is Euclidean, or this basic idea that we've all known, we've all studied, but now it adds on a smaller space, so to speak. And the smaller space isn't necessarily in size as far as what we can visualize and see, but it's as far as a different set of things. So I guess if you've taken some math classes and you've gotten pretty far along in math, we can talk about infinite numbers. And if you're going to just take, for example, the integers, you can see, okay, I have this infinite amount of integers, but if I just want to take the positive integers, we have a smaller group of integers, and it's still infinite in size, but it's been reduced in size at the same time. So that's what we mean by this idea of smaller. Is it's infinite in size, but it's just a little bit more narrowed down.